Good morning, gentlemen. Today is Monday, June the 1st, and today we're going to continue our discussion of modern physics. And today we're going to continue that discussion by looking at what we call the quantum theory. Now, most of you should have at least some small memory of quantum theory from your discussions with Mr. Leonard in chemistry class. Essentially, what it deals with is the amount of energy that it takes to get an electron to jump from a lower energy level in orbit around an atom to a higher energy level. All right. Do you remember that when an atom absorbs energy, its electrons become excited? They jump up to a higher energy level. When they jump back down, they release that same amount of energy, and that energy is emitted as light. Now, in chemistry, you use this for atomic spectra and a number of other different things. Each atom will give off a certain wavelength of light, excuse me, as well as a couple of other things. Now, in terms of the quantum theory, essentially what it says is that each electron that jumps up or down is either absorbing or emitting a very specific discrete amount of energy, and any less is not going to work, and any more is not going to make it jump any higher. Okay, it's like electrons are almost like on a staircase. They jump that you can only take one step at a time. You can't take a half a step or 3.5 steps or a step and a half. Right? It just doesn't work that way. So the guy who originally came up with this idea of the quantum theory is a guy by the name of Joe Planck. Now, Planck was a German physicist who realized that because each atom was giving away or giving off certain wavelengths of light, that each one must have different energy levels. In other words, their first energy level and their second were different distances apart. So if you compared, for example, hydrogen and mercury, they would have different amounts of energy required to jump from the first to the second energy level. And so his theory explained the idea of electron excited atoms releasing light. And he realized that energy can only be absorbed or emitted in discrete packets that he called quanta. All right, which is essentially a take on the word quantity. Now, Planck also realized that there was a relationship between the amount of energy that was absorbed or released and the frequency of light that was emitted. And he found that relationship was a direct proportion, so that if you graph energy on the y-axis and the frequency on the x-axis, that you would end up with a direct proportion. But remember, there was always that first portion where no light was emitted, and this right here is the threshold frequency, f sub 0. Okay, so what Planck realized is that because this is a direct proportion, E must equal some slope number, which he called h, times the frequency. Now, h is today called Planck's constant, and it's equivalent to 6.63 times 10 to the negative 34th joule seconds. Now, that number can be found on the front page of your handy-dandy reference tables. Planck's constant is about 2/3 of the way down. You can see it there. Planck's constant, h, 6.63 times 10 to the negative 34th joule seconds. All right. So the numbers there on your reference tables, you don't have to memorize it. Okay. So what exactly or how exactly does this quantum theory of Planck's work? Well, it's dependent upon a discrete packet of electromagnetic energy that we call a photon. Now, oftentimes people think about photons in terms of light energy. But you have to realize it's not just visible light that can do this. It's any kind of electromagnetic energy. So microwaves can do it, infrared, ultraviolet, radio waves, X-rays, you name it. Anything that you find on that table on the second page of your reference tables here in the electromagnetic spectrum. So any of these various forms of electromagnetic energy can or is composed of photons. And we define photons as a particle of light, or more accurately, a particle of electromagnetic energy, having both energy and momentum. All right, we'll get to the momentum part later. Now, because the energy of this photon is equal to Planck's constant times frequency, and frequency is equal to the speed of the particle divided by its wavelength, we can also say that h times c over lambda, where c is the speed of light in a vacuum, and lambda, of course, is the wavelength, is another way to write Planck's formula for electromagnetic quanta. Now, a couple of things. First, this formula is actually found in the modern physics box of your reference tables. The energy of a photon is equal to h times f, or h times c over lambda. All right, so they're there. And again, you don't need to memorize them. All right, that brings us to example number 1. All right, for example number 1, we have the question, the energy of a photon is 2.11 electron volts. 3 questions, or 3 problems here. Determine the energy of the photon in joules, determine the frequency of the photon, and determine the color of light associated with the photon. So, I'm going to give you a minute to write this down, but remember that the relationship between electron volts and joules is found on the front page of your reference tables. 1 electron volt is equal to 1.60 times 10 to the negative 19th joules. Okay, so there it is. All right, so that's the first part. All right, all we have to do here is convert electron volts to joules. In order to do this, we take the original energy value, which is 2.11 electron volts, and we simply multiply that by 1.60 times 10 to the negative 19th joules, because that's the value of 1 electron volt. And so 2.11 times 1.60 is going to give me 3.38 times 10 to the negative 19th joules as my energy. There should be a 10 in here. I'm not really sure how I missed that. Sorry. But 3.38 times 10 to the negative 19th joules. And that is the amount of energy that I have. Now, the second part of the question asked you to determine the frequency of the photon. And so if energy equals Planck's constant times frequency, then frequency is going to equal energy divided by Planck's constant. Well, we just calculated the value of the energy as 3.38 times 10 to the negative 19th joules. We divide that by 6.63 times 10 to the negative 34th joule seconds, which we looked up on the front page of the reference tables. And that gives me a value of frequency of 5.09 times 10 to the 14th hertz. Now, the last question asks you to determine what color this is, or what kind of light this is. And if you go back to the electromagnetic spectrum here and look down here at visible light, you'll find that the red light is starts with a frequency of 3.84 times 10 to the 14th joules. Hertz. And so therefore, it's lower than red. It has a smaller frequency than red. So if you look at what's just below that, you'll find that it's the infrared light. Okay, so the color of this light in this case is not really a color, not a visible color anyway, but it is infrared light. 5.09 times 10 to the 14th hertz is infrared light. Okay, so after Planck was doing his work, another very famous scientist by the name of Joe Einstein came onto the picture and started playing around with this. As we talked about on Friday, Einstein is responsible for the photoelectric equation. And essentially, this equation is a mechanism of trying to figure out the relationship between the energy that is striking a metal and what happens to that energy in the end. Well, it turns out that two things happen to the energy. First, some of it is used to release the electron. All right, and remember the other day we called this the work function. The rest of that energy is used to convert or is converted to the electron's kinetic energy. So essentially what's going on is this. The energy is equal to the kinetic energy of the electron plus the work function, all right? And if you want to rearrange this equation to calculate the value of kinetic energy, you'll find that all you got to do is subtract the work function from both sides, and you get Ke max equals HF minus the work function. All right, this is the energy of the photon. This is the energy that it takes to release the electron, and this is the kinetic energy of the electron that's been released. All right. So those are the three sums that you see in this particular question or equation. Now, this equation is not, I repeat, not found on the modern physics or in the modern physics box for your reference tables. And so if you want to use this on a review activity or a homework assignment, you should definitely write it down now. All right, Ke max equals HF minus W sub O. That brings us to example number 2. The stopping potential required to prevent current through a photocell is 3.2 volts. Calculate the maximum kinetic energy of the photoelectrons with a frequency of 5.09 times 10 to the 14th hertz. So again, we're dealing with infrared light here as they are emitted. All right, so we want the kinetic energy. Now, we already know that the formula here, the formula is going to be Ke max is going to equal HF minus W sub 0. Now, the thing is, we're not given the those values, but we are given the voltage here. So, what that means is we have to find a way to convert from voltage to work. Do we know a formula for this? Well, it turns out we do. If you go to the electricity section on your reference tables, the third formula from the top is V equals W over Q. Now, we're looking for W. We've got V. What's Q? Well, it turns out that Q is the charge on an electron. All right, so negative 1.60 times 10 to the negative 19th coulombs is the charge. All right, and so we can use that information and the voltage to calculate the work function. We can use the frequency and Planck's constant to calculate the total energy, and we can use that to calculate the value of the maximum amount of kinetic energy. All right, so let's go through this, shall we? All right, we know that our voltage value is 3.2 volts. All right, that's what was given to us in the problem that we saw in the previous slide. We know that the charge on a single electron is negative 1.60 times 10 to the negative 19th, and this should be coulombs, not joules. All right. We know that work is equal to volts times charge, voltage times charge, and so, or voltage equals work over charge. We got that formula from the reference tables. And so doing a quick little bit of arithmetic here, we can calculate the value of the work as 3.2 times 1.60 times 10 to the negative 19th. And that gives me a total amount of work of negative 5.12 times 10 to the negative 19th joules. All right, so there's my work function. Now, the energy value is equal to Planck's constant times the frequency. We were given the frequency of light as 5.09 times 10 to the negative, that's not right. It's not negative 19th, it was 14th hertz. Sorry about that. All right, so this should be 14th hertz. But the calculation is correct here. 6.63 Planck's constant times 10 to the negative 34th times 3.37 times 10 to the negative 19th, 5.09 times 10 to the 14th gives me 3.37 times 10 to the negative 19th joules. Then I can calculate the value of the maximum amount of kinetic energy, and that's the energy value of 3.37 times 10 to the negative 19th minus the work value, which is negative 5.12 times 10 to the negative 19th, and that gives me a kinetic energy of 8.49 times 10 to the negative 19th joules in this case. Okay? So that's the kinetic energy of the object. Now, moving along. Example number 3. A similar kind of question, but this time given different information. A photocell uses a sodium cathode, which has a threshold wavelength of 536 nanometers. Now, wavelength is not going to be terribly useful for us. We need to convert that to frequency. So the first thing I'm going to do is look up what is a nanometer on the front page of the reference tables. And nanometer is a 10 to the negative 9th. So this is 536 times 10 to the negative 9th meters, or 5.36 times 10 to the negative 7th meters. So there's my wavelength. Find the work function here. All right, well, the wavelength can be used to calculate the value of the frequency. All I got to do there is divide the speed of light by the frequency, and that will give me, by the wavelength, and that'll give me the frequency. So we know the wavelength is 536 nanometers, which, as I told you a moment ago, we can immediately convert to meters and call it 5.36 times 10 to the negative 7th meters. Now, holy Christmas, what is going on here? So in this case, the speed of light is going to equal the frequency times the wavelength. All right. And so therefore, since I know the value of the wavelength and the speed of light is also a constant found on the very top of the reference tables in the list of physical constants, the speed of light in a vacuum is equal to 3.00 times 10 to the 8th meters per second. All right. And so if that's the case, I can calculate the frequency as c over lambda, which gives me 5.60 times 10 to the 14th hertz. Now, just for kicks and giggles, although it doesn't ask what color is that, go to your electromagnetic spectrum, and 5.60 is going to be somewhere in the green spectrum. So this is green light. Now, the other aspect to this question, all right, find the work function. Well, the work function is the amount of work or energy that's required to release the electron. And so the way that we can do this is assuming that the kinetic energy of the electron is zero, right? It's not moving, it's just been released, not given any kinetic energy, then the work function equals h times f. In this case, the work function is going to equal Planck's constant times the frequency we just calculated. So 6.63 times 10 to the negative 34th times 5.60 times 10 to the 14th gives us a work function of 3.71 times 10 to the negative 19th joules. Now, the last part of the question says, if ultraviolet light with a wavelength of 3.48 nanometers falls on sodium, what is the energy of the ejected electrons? So, in this case, I can immediately take that 348 nanometer wavelength and convert it to meters, and it becomes 3.48 times 10 to the negative 7th meters. Now, using the same formula that I used up here, C equals F times lambda, I can divide the speed of light by lambda, and that's going to give me the value for frequency of 8.62 times 10 to the 14th hertz. Okay, now, there we go. So next step, calculate. So that's the frequency. The next step is to calculate the value of energy, which is Planck's constant times the frequency. So 6.63 times 10 to the negative 34th joule seconds times 8.62 times 10 to the 14th hertz gives me an energy value, E, of 5.72 times 10 to the negative 19th joules. So this number is 5.72 times 10 to the negative 19th. The work function is 3.71 times 10 to the negative 19th, and that gives me a kinetic energy value of 2.01 times 10 to the negative 19th joules. Okay, moving along. For our next trick, let's talk a little bit about a guy by the name of Arthur Compton, right, who is responsible for discovering what we today call the Compton Effect. What Compton realized was that when a photon actually collided with a particle, that very distinct and measurable quantities came out of it. All right. Usually, under ordinary circumstances, the energy of a photon is completely absorbed and given to the emitted electron. All right. So ordinarily, the energy of the incident photon is completely absorbed. So the HF value is converted completely to kinetic energy and the work function. So it's all energy. But Compton discovered that photons of X-rays, which have a very high frequency and energy value, eject electrons, but they also give off low frequency radiation. All right, and so therefore, not only was energy observed, but momentum was observed as well. All right, this immediately started thinking, or got him thinking, there must be a particle in here. Excuse me. All right, and this is, again, today known as the Compton Effect. Now, it only happens under certain circumstances, all right, X-rays specifically, high frequency and high energy, but they give off both energy and momentum. Now, using this and using the idea of the conservation of momentum, Compton realized that a photon has to have momentum. If it's a particle, it's got to have momentum. And since the momentum of a particle is equal to mass times velocity, he couldn't really do that very specifically, and the reason for that is that the photon has an immeasurable mass. It's very, very small. But Compton was able to calculate the value of the momentum of a photon as the energy of the photon divided by the speed of light. Now, since the energy of a photon is Planck's constant times frequency, and the speed of light is equal to the frequency times the wavelength, he calculated that the momentum of a photon was equal to Planck's constant divided by the wavelength of the light that the photon was experiencing. Okay. Now, for very teeny tiny particles, the wavelengths can be very large, all right, quite large, because the momentum of this photon is exceptionally small. I mean, theoretically small, immeasurably small. Okay, but whoops. But for larger particles, we have a different story, and we'll get to that in just a second. Now, the next guy in our little history lesson here is a guy by the name of Joe de Broglie, and he discovered what we call de Broglie waves. Now, when we talk about a photon having a very, very small, immeasurably small mass, but a wavelength that we can actually calculate or even measure, all right, de Broglie did a little bit of reverse psychology here and said that if photons have momentum, as per Compton's work, then particles must have a wavelength. All right, think about that. All right, if photons have momentum, then particles must have a wavelength. And so he took Compton's formula for momentum, h over lambda, and rearranged it to say that lambda must equal Planck's constant divided by the momentum. And since we know that momentum is equal to mass times velocity, this gives us a formula to calculate the momentum of a particle traveling in a transverse wave, a sine wave, up and down. Now, if for little particles, we can easily measure wavelengths and all of that kind of stuff. But for large particles, think baseballs, all right? These wavelengths are too small to be noticed or even detected. But for particles as large as electrons, doesn't that sound weird saying as large as electrons? We have been able to calculate them. All right, we know what the de Broglie wavelengths are for electrons. All right, and that's fairly exciting news because we're showing that particles actually can travel in a transverse wave. Now, that brings us to example number 4. In this case, I'm going to ask you to calculate a de Broglie wavelength. What is the de Broglie wavelength of a 0.145 kilogram baseball leaving a bat with a speed of 38.0 meters per second? All right. So take a moment here and write this down. And of course, make yourself a laundry list. All right. What do we know? Well, we know that we're looking for wavelength. We know that we've got mass and we've got velocity, or at least speed, right? And we know what Planck's constant is. And so therefore, we should be able to calculate the wavelength quite easily. So how do we do this? Well, let's have a look. All right, we start, of course, by making our wavelength or writing down all of the things that we need to know. The wavelength is our big fat question mark. The mass is 0.145 kilograms. The speed is 38.0 meters per second. And Planck's constant, of course, right from the reference tables, is 6.63 times 10 to the negative 34th joule seconds. The formula to calculate a de Broglie wavelength is lambda equals h divided by mass times velocity. And I'm not going to go through all the calculations here, but 6.63 times 10 to the negative 34th divided by the product of 0.145 and 38.0 gives me a wavelength of 1.20 times 10 to the negative 34th meters. That is a really small distance. Okay. Now, for homework, gentlemen, I would like you, and I will post the homework sheet on the portal. But I would like you to do homework questions 1 through 4 on the homework sheet. All right. So have a look at those questions. and I will post when it's going to be due. I don't have my calendar sitting right here in front of me, so I'm not exactly certain when that might be. I think actually I believe it's going to be tomorrow at the end of day. So at the end of June 2nd, these questions will be due. All right, fellas, have a great day.